As we know, atoms share electrons to make molecules. And so we can think about these molecular systems in the paradigm of quantum mechanics like we have been thinking about atoms. So to do this, we're going to take the same sort of approach that we did for multi-electron atoms. We're going to start with the simplest possible molecule, which includes 2 protons and 1 electron. So this is an H2 plus ion. And notice that we have a nuclear repulsion. We have an electron attraction to both nuclei. And we have a 3-body problem, just like we did when we had more than 1 electron and 1 nucleus. So we're going to have to use approximations to do this. So what we're going to do is solve this problem by making some approximations. And one of the approximations that we make is called the BornOppenheimer approximation. In this approximation, we're going to assume that the distance between the nuclei is fixed. So this is a constant fixed value. We'll just use a capital R for that. The reason we do this is because the nuclei are so much heavier than the electron that the electron is going to move many picometers when the nuclei only move a very small amount. And so the movement of the nuclei compared to the movement of the electron can be ignored. And so we can think of this as a fixed value. The nuclei stay at a fixed distance because they move so much more slowly than the electron. And so on the time scale that the electron's moving, we can ignore the motion of the nuclei. This is called the Born-Oppenheimer approximation. And it basically states that we ignore the nuclear motion relative to the electronic motion, and then solve the problem for different fixed values of the nuclear distance. So just like we used the hydrogen atom wave functions as the basis set for constructing trial wave functions for multi-electron atoms, we're going to do the same thing here and use solutions to the hydrogen ion molecule as a basis set for constructing trial wave functions for multi-electron molecules. Notice, though, that these solutions depend on what distance we decide to set the 2 nuclei away from each other. And so if we solve the problem for the nuclei being very far away from each other, the energy is very close to 0. And if we move those nuclei closer to one another, the energy goes down to a minimum. And then as we begin to move the nuclei closer and closer and closer to one another, the energy goes up. And so we get this typical binding curve where we have a minimum energy, and that defines the equilibrium distance. The distance between the nuclei where we get that minimum energy is where we would expect the nuclei to be relative to each other. And as we get closer and closer, the nuclear repulsion begins to get stronger and stronger, and we end up with a repulsive wall over here at distances where the nuclei are too close to one another. As we move them further and further apart, then it's just as though we have a hydrogen ion and a hydrogen molecule, and we call the energy out here where the 2 nuclei are not interacting as the 0 energy. So the wave functions at this energy minimum are going to be the wave functions that we use for our basis set. And then we're going to use those to form trial wave functions for the hydrogen molecule, which contains 2 electrons, maybe the helium molecule, which would contain 4 electrons, etc., etc.